Hello, welcome to this video, which is a continuation of my previous videos on dynamical systems, in which we solve systems of ordinary differential equations. So far, we've just been solving two ordinary differential equations. It can progress to systems of three ordinary differential equations, 4, 5, and 6, and so on. You can have multitudes of them, but normally we will just be used to solving systems of two or maybe three at the most, but possibly four as time progresses. Um, Again, this system, x dot equals x plus y and y dot equals minus 5x minus 3y, is from this book called Nonlinear Ordinary Differential Equations, An Introduction to Dynamical Systems, which is the third edition by the authors D.W. Jordan and P. Smith. So we're actually going to attempt example 2.7 out of this book. I'm going to use a similar method to what the authors have used, but hopefully, well, I'm hoping this is going to be more brief than previous videos I've done, so I think we'll make a start. So as you can see, we've got these two equations here, which can be written, and I'm going to write them as x dot equal to little x dot. So that's capital X dot, which is equal to the vector which contains x dot or small x dot, small y dot, and that's equal to, well, the first equation, x dot is equal to x plus y. That's the same as 1 and 1 in that matrix. We don't forget to put our x and y vector in there. And then for the y dot vector, we've got minus 5x minus 3y, or if you like, minus 5 minus 3, like that. Now, what we do straight away, if you remember, is you can check to see if the determinant of this is or isn't equal to 0. So if we let a equal to 1 minus 5, 1 and minus 3, like that, then we see the determinant is equal to 1 times minus 3 is minus 3, minus 1 times minus 5, which is minus 3 plus 5, which is equal to 2, if I've got that right. 1 times minus 3 is minus 3, minus 1 times a minus 5, so that becomes plus 5 minus 3, which is 2. So we can see, in this particular case, this determinant is non-zero, so we can seek to find a solution, generally at the origin for this kind of case, by finding the characteristic equation associated with matrix A. So find the characteristic equation. I think my pen could be beginning to run a bit dry, so apologies for that. So find the characteristic equation. What do we do? Well, as I always say, find the determinant of lambda I minus A, and that's equal to lambda times the identity matrix minus the entries that we have in this matrix. So in actual fact, that is just going to be, and I'm missing a step out now, because you should have cottoned on to this method from the previous 2 or 3 videos. So we have lambda minus 1. We're subtracting this matrix A, so we get a minus 1 here. If you go through the steps that I showed you in previous videos, you'll find that that comes out to be lambda minus 1, that becomes a minus 1, that becomes a plus 5, and here we have lambda plus 3, and that's got to be equal to 0. Okay, so if this is equal to 0, then it means that lambda minus 1 times lambda plus 3 minus a minus 1 times 5 is also equal to 0. And there we are. So what does that come out to be? So we've got a lambda times a lambda is a lambda squared. A lambda times a 3 is plus 3 lambda. Minus 1 times lambda is minus lambda. And then we've got minus 1 times 3, which is minus 3. And that is plus 5 equal to 0. So this simplifies to give lambda squared plus 2 lambda. And 5 minus 3 is just plus 2, and that's equal to 0. Now the question is, can we factorise that quadratic equation? This is the characteristic equation for this matrix up here. Well, no, we can't really factorise it very easily, because if we use a quadratic formula, lambda equals minus b plus or minus the square root of b squared minus 4ac over 2a, then we find that we've got, well, the b is equal to plus 2, so that becomes minus 2 plus or minus the square root of b squared is 4 minus 4 times this coefficient here, 1, times 2, which is minus 8, over 2a, which is just 2, because the coefficient of a is just 1 in that particular case there. So we'll just erase that. This simplifies to give lambda is equal to minus 2 plus or minus the square root of minus 4 over 2, which is just equal to minus 2 plus or minus, well, the square root of 4 is 2, and the square root of minus 1 is I, so it's plus or minus 2i over 2. This means that lambda is equal to minus 1 plus or minus I. Right, so there are two roots for lambda. They're both complex. So, in fact, we can write them down like this. Lambda 1 is equal to, we'll take minus 1 plus I as lambda 1, and lambda 2, which is the other eigenvalue, is minus 1 minus I. Right, okay. So, considering, so if we consider lambda 1 equals minus 1 plus I, then the matrix formed by substituting minus 1 plus I into this part of the matrix here, we'll call that B1 is equal to, well, minus 1 plus I, so we've got minus 1 plus I, minus this 1 here. The minus 1 here stays the same. We'll just complete that matrix. We want the x and y vector in. So this 5 stays the same. And of course we've got minus 1 plus I plus 3. So minus 1 plus I plus 3. So we just tidy that matrix up a little. So we get that B1 is equal to minus 2 plus I. And I'll just, what I've done is, well, we'll just proceed with this. Minus 1, 2 plus I, and 5. So that's what we get for that matrix there. Now what I've done, because I think this is easier myself, I've taken the minus sign out of this so that we have a negative complex conjugate of that. So we've got B1 is equal to, oh, and by the way, the x and y vector should be in there. Let's write it in again. So we've got minus 2 minus I there, minus 1, 5, and 2 plus I. And let me just change pens. See, that's, we'll have to proceed with this pen for now. But I do have a spare one if I need it. That's blue. So now this is a bit more complex than it's literally complex in fact, but this is more complicated than what we had in the previous video because we now have the complex number I. Now to solve two simultaneous equations like that, which are actually multiples of each other, but we've got to show it. To solve each of these simultaneous equations, which is what they are, we need, what we're going to do is we're going to multiply everything in the top line by 5 and everything in the bottom line by minus 2 minus I. So what you get if you do that is you obtain B1 is equal to, well, 5 times minus 2 minus I you can just leave as minus 5 times 2 minus I. Minus 1 times 5 is just minus 5. And then we've got our xy vector there. And then we multiply everything here by this. So here we get minus 5, 2 minus I. And what do we get if we multiply minus, in brackets, 2 minus I by 2 plus I? Well, let's just write that down and see what we get. I'll write in green here, and hopefully you should be able to see it. So if you multiply minus, I'm going to take the minus right hand side of the bracket, 2 minus I times 2 plus I, we get minus, in the bracket, 2 times 2 is 4, 2 times plus I is plus 2I, minus I times 2, or if you like 2 times minus I is minus 2I, and minus I times I is minus I squared. So what's that? Well, you should be able to notice straight away that that cancels with that. And what is minus I squared? Well, you should be aware that minus I squared is, or I squared is equal to minus 1. So minus I squared equals 1, right? So we've got 4 plus 1 in the brackets, and of course adding together 4 plus 1 and multiplying by this negative sign outside gives -5. So what we've got here is -5. Now I'm just going to rub this bit of rough working out. So hopefully you've got that. And lo and behold, you can see, or you should be able to see, that we've got two equations here which are identical. They're still multiples of each other, but in this case identical. So in actual fact, if we take either of these equations, the implication is that, I'll just change pens again. We've got -5, and by the way, all of this has to be equal to 0, which I keep forgetting to write in. Right? So we've got -5 times 2 minus I, -5. In fact, actually, if we're multiplying out by the x and the y's, we've got -5 times 2 minus I times x. So it's this entry here multiplied by that. And then we've got the -5 times the y, which is -5y equal to 0. Now, we can simplify this by dividing by -5 to get 2 minus I times x plus y. And I'm going to check with my notes to make sure that we haven't made any mistakes. And yes, that is correct. So 2 minus I times x plus y. Now, how do we work out what the eigenvector is from that? Because we've still got this irritating complex imaginary number in front of the x value, the x variable. So we've got a coefficient of 2 minus I, where I is imaginary. We do just the same as we did before. We, for example, can let x equals 1 and y equals minus 2 minus I. Right? Because when we substitute x equals 1 back into this, 2 minus I times 1, and we substitute the minus 2 minus I into that, then what we get is 2 minus I minus 2 minus I, which is equal to 0. Right? So we know that our eigenvector is composed, or one could say comprises of, the x component, which is 1, and the y component, which is minus, in brackets, 2 minus I. So we'll write down our first eigenvector. And we'll leave that bit on the board. So let's just rule this off. So an eigenvector, therefore, an eigenvector v1 is equal to some constant, which we'll call c1, times the eigenvector 1 and minus 2 minus I. Right. And that's associated with the eigenvalue lambda 1 equals -1 plus I. Now, consider lambda 2 equals 1 minus I. Well, then we get another matrix, B2. So if you remember, the matrix that comes after this is the determinant part from which you form the characteristic equation. So if we substitute lambda minus 1 into, I'll write it down here. So B was equal to lambda minus 1 minus 1 5 lambda plus 3 times our vector xy. That was B, right? So if we substitute 1 minus I in for lambda there, we get B2 equals 1 minus I minus 1. Minus 1 stays as it is there. And we've got 5, 1 minus I here, plus 3. So you can just put brackets around those to show that they're separate entries from this and this. So B2 is equal to a simplified matrix of, and I'm forgetting to put my xy vector in again. So 1 minus 1 is 0, so that's just minus I. And I'll double check that I am getting the right values here. Now, let me just have a... We should actually be getting... Oh yeah, sorry, that's minus 1 minus I. Do you see how I make mistakes with plus and minus signs? I've forgotten to include the minus sign in front of the 1. Given that we've got lambda 1 is equal to minus 1 plus I, and lambda 2 is equal to minus 1 minus I. This is the case for lambda 2, which is minus 1 minus I. So I'll just put that minus 1 in there. And we've got a minus 1 there. So, simplifying this matrix, we get minus 1 is minus 2. Minus I, minus 1 over here, 5, and minus 1 plus 3 is 2, and the minus I stays the same. So we've got that for B2. And I'm just wondering, because I tidied that up and I said let B2 be equal to minus 2 plus I. So I've just taken the minus sign out of this first entry and put it in front of the brackets. That still stays as minus 1. 5, and that just stays as 2 minus I. There. Let's just write that in. 2 minus I. Okay. So, if we just clear the board. Right, so we do pretty much the same as we did with B1. So we multiply this first entry by 5. So basically what we're going to do is we've got our x and y vector there. So I probably should write this down. We multiply the first equation in the matrix, in the last matrix I'll say, by 5, and the second by minus 2 plus I, so that we get the following matrix. So we've got B2 equal to minus 5, 2 plus I. So minus 2 plus I times 5 gives you minus 5, 2 plus I. Minus 1 times 5 is just minus 5. And then we've got 5 times this, which is just minus 5 times 2 plus I. And then we've got 2 minus I times 2 plus I. But if you remember what I said, and I shall do this again so that it reinforces it for you, we've got minus 2 plus I times 2 minus I. So this is equal to minus 2 2's are 4. 2 times minus I plus 2 times I is just 0. And then you've got plus I times minus I, which is minus I squared. And that's equal to minus 4 plus 1, which is equal to minus 5. If you multiply by the negative sign outside the brackets. Right? So, what we can write up here, again, is minus 5. I'm going to change to a blue pen because I need, we'll use this and see how this goes. So, and of course, this has got to be equal to 0. In fact, I forgot to put the x and y vector on the end. X, y equal to 0. This means that we can simplify both of these equations to get 2 plus I x plus 1y. And so what they did in the book was to choose x to be equal to 1 and y to be equal to minus 2 plus I. Or if you like, equal to, in brackets, minus 2 minus I. So you see we had a minus, in brackets, 2 minus I there. This time we've got minus the complex conjugate of that. So we can write down that V2, this is our second and final eigenvector, is equal to C2 times, in brackets, 1 minus 2 minus I. And Jordan and Smith actually do write it like that instead of taking the minus sign outside and absorbing it into the C. which I probably would have done, or I might have done it slightly different to them. And again, that would have been probably admissible. And of course, you would normally have initial conditions, which would determine the actual value of the constants anyway. So a general solution, therefore, a general solution is x, and that's equal to our x and y values in the appropriate vector, not x dot or y dot, just x and y this time, because those are our solutions. So that's equal to, well, the first vector is c1, 1, and I'm going to write that as minus 2 plus I times e. Now this time we know that lambda 1 is minus 1 plus I. So we put minus 1 plus I, put brackets round it, and then t. And I haven't got room, I don't think, to fit the rest on there. So I'll just finish this off by adding on C2, 1 minus 2 minus I times E. Well, the eigenvalue associated with this eigenvector is, where is it? Well, it's minus 1, lambda 2 is equal to minus 1 minus I, isn't it? Minus 1 minus I. So that would be bracket minus 1 minus I times t. Now, because this final solution here is in terms of, not just in terms of exponentials, but written in terms of exponentials to the power I, you can actually rewrite the equations in sinusoidal form multiplied by an exponential that decreases. So we're going to just, I'm just going to call this x. That's the vector x, and that's equal to, well, actually, no, we'll stick to writing, x is equal to, well, x is equal to c1 times 1 times this exponential part. So that's c1 e to the minus t times e to the I t. You see, I've just split this up into the product of two exponentials. So I'll say this again. I've split this exponential up into the product of two exponentials, e to the minus t times e to the it. And then we've got plus c2 times minus 2 minus I e to the minus t e to the minus it, right? So let me just, there we are. I think I picked up the wrong pen again. Right. And y is equal to c1, and in brackets, minus 2 plus I e to the minus t e to the it plus C2 I've made a mistake. That should just be C2 times 1 times that. I do make mistakes. E to the minus t, e to the minus it up there, and then C2 times that is minus 2 minus I e to the minus t e to the minus it. Now I'm writing it like that because that can be simplified, and you can write x is equal to e to the minus t times, in brackets, c1 e to the it plus c2 e to the minus it, and y equals e to the minus t times c2 minus 2 plus I e to the it. That should be c1, shouldn't it? Plus c2 minus 2 minus I e to the minus it. Now, what Jordan and Smith actually write this as eventually, and you can work this out. It takes a little bit more algebra and trigonometry and knowing your trig functions, but x can actually be rewritten as e to the minus t times c1 cos t minus c2 sine t, and y can be rewritten as e to the minus t, and this is a little bit lengthier, so we've got 2c1 plus c2 times cos of t plus c1 minus 2c2 sine of t, and that is basically the final solution, or the two final solutions to that system. So apart from the little hiccups and occasionally making little mistakes, again, I hope I've explained that reasonably well, and that you've been able to follow me, and that you've learnt something from this tutorial, this video, and again that you will not only revisit previous videos that I've uploaded, but that you will stay tuned and keep on coming back to visit future videos as well. So thank you very much for listening, and see you soon. Okay, bye.